All right, happy St. Patrick's Day. I'm about as Irish as an Australian, but what we've got here is lots of Irish mathematics. We're going to talk about the quaternion, or the results of the quaternion by Mr. Hamilton. And there's a museum for this in Dublin. And that should be a museum because this is an amazing discovery. More amazing perhaps than the complex numbers that Euler found. And this is true both for mathematics and physics. Changed the world. So we're going to see some of the things you can do, including the crazy thing theorem that I'm sort of leaving as a problem a little bit. And there are a couple of things here that the problem will mostly be the Irish mathematics. But I don't mean to imply that there's only one nationality here. The other way of looking at matrix analysis and spectral decompositions and things like that, and this is the main line one, but I've got it nicely dressed up so it's much more efficient and better to understand. It's got some geometry in it to help. I would say was German and French, so and English. So we really have a fairly diverse population if you just count Europe. Meanwhile, around other parts of the world, the same sort of things are coming along here and there, but not with quite the amount of noise, that is volume, that the European Renaissance brought forth. Anyway, diversity is good because you look at things differently and you start to discover new things that sometimes nobody else noticed. All right, so after we get done with just reintroducing, this is partly a review of the connection between the classical two-dimensional harmonic oscillator and the quantum two oscillator system, but there you're really doing quantum mechanics as far as the mathematics goes. And after we get done with that, and then this is going to take a good bit of time here to go through, and I really would appreciate questions at any point here. This is something that a high school student should be able to understand. And so is this. This is just a little more sort of abstract. We're going to use it for doing both problems at once. And we have some animations, I think, that I've really beat on and TTC's worked hard on, and they seem to work well, so we should have no problem doing the three colors here and then maybe mix them a little bit before we're done today. In any case, the featured beast here is the word mechanical. And the mechanical analog that I'm talking about that takes care of what I call the quantum phasor. And that's this machine right here that there are really only two of them in the world. One's at the Joint Institute of Laboratory Astrophysics, where I was fortunate enough to write a paper that had a crude sketch of something like this. And the instrument maker said, wow, that's cool, I gotta make that. And he proceeded to take pieces out of broken lasers and things like that and built a huge one of those with ring all the way around, ring all the way around, ring all the way around. It's just an amazing looking thing, and it sort of worked, but as soon as I started playing with it, I realized, oh my gosh, I wish I'd just used quarter rings like this one here, because then it could rotate all the way around. It sort of would help it get stuck. But anyway, it's a nice piece of decoration, and it's still in the library up there at the top of the tower in Gillett. This one, I did most of the machining at Georgia Tech. And we're going to redo it because what it really needs is a clear sphere with a vector in it that represents spin. So that I don't have to say, hey, there's a vector inside that sphere. And I'll be saying that a lot today if we make a connection between this and everything that happens in the dynamics of the quantum spin. So let's just real quick get started here. And the thing I want to look at is the review, and that is the connection between this first order differential equation, it's the first derivative, and a matrix of complex numbers, but only the off-diagonal is complex, and that's the same thing true over here, but it's kind of weird to have a complex number there. That requires some magnetism. That's not something that most people that do this kind of problem would see right away. In any case, once you do that, then these two are essentially the same thing. And we showed that by taking it apart, actually putting it together. It depends on which side of the thing you're looking at. And the idea being that as soon as I use units where I don't have to have that tiny h-bar in there, then they really start to look alike. And the idea is that you square I, you get a minus. If you square d dt, you get a dt squared. That's exactly what you've got here. There's a minus sign on that one. So that's the real connection there. And the idea is that this thing is that thing, okay, which is that thing. So we have a bunch of different variables for working on this side of the thing. But this one is neat because these parameters here are frequencies. All of the things that come out here are frequencies squared. You can see they're all quadratic expressions in there. Okay? So that makes this problem a clumsy way to look at. This is a neat way to look at. Take advantage of what is simple about quantum mechanics and make it happen in the classical mechanical world. So that is being connected down here and sort of dropping off of the screen there. And that is probably because I have not yet set this one in its right mode. So I'll go ahead on this one and do that. Let's get this one working the way it should. That means, and I have to look at the particular version here, take me to the full screen. Thank you. Okay, so the last thing that I didn't mention last time, this is not part of the review, this is something new that we're going to tackle today. And the question is, I could write the quantum Hamiltonian as the square root of the classical one. But how in the heck do you take the square root of a matrix? Okay? So, as I say at the bottom of the slide, stay tuned. That's what we're going to do when we do the spectral decomposition routine for diagonalizing matrices. Something that maybe some of you don't really need to know, but it's so beautiful you really should see it. Okay. This is the other thing that we looked at a bit at the end of last lecture, and that is this weird sort of decomposition. It's not a spectral decomposition, and we'll get a definition of that shortly, but it is certainly an important one of just writing a matrix in terms of things that have simple properties. And if I take these two together, have sum and have difference, I make a unit matrix over here, and then I make a thing that has a minus, is an anti-symmetric diagonal matrix. Well, those are the famous Pauli spinor matrices, but they're also connected with a factor I to the, I would say, more famous, because there are more people that do all kinds of mathematics with the quaternions. But this is, for the physicists, the most famous. Most physicists really don't care about quaternions, and some of them don't even know what they are. I would say half at least. But in any case, the connection is right here in 1843, not 1927. This is way earlier. Hamilton has a vision, so to speak, as he's crossing a bridge in Dublin, that the way to complete the complex number business and hyper-complex and make it so it can do three-dimensional stuff is to do four-dimensional stuff. Get four numbers here. He kept looking for three numbers that would do the trick for him and couldn't come up with anything. In any case, his notation is I, J, and K. The same notation that they use in Cal 1 through whatever for unit vector X, unit vector Y, and unit vector Z, right? How many people have run into I, J, and K, right? Well, that's Josiah Willard Gibbs, the American physicist that went over to Europe to learn what all those great guys were doing. And he saw this quaternion thing I'm going to show you today. And he said, boy, that's a little too much for those Americans. They don't want to get that. It's too complicated, you know. But boy, I could use that I, J, and K in kind of a way. And that's when his notation got started. And so this fat pen notation is an American thing, very much. So anyway, we are using a no notation right here, as I said last time. This A and D stand for asymmetric diagonal, which that is. The B stands for being balanced off diagonal or bilaterally symmetric. And then this thing has a whole bunch of C's. Chirality mainly is something that gets things circular. It makes current, okay, happen in quantum systems. So that's thing. Now, if you're just going to play with these two, then you don't need Hamilton. This thing, and it's appropriately green, also because it's Irish, and it really gets things going. Okay. If you just have these, you might as well stick to the complex numbers. You don't need all this fancy stuff, because this is all in one plane. And all it does is take your potential and rotate it. Okay? So, that's what we're going to try to understand today, is that. Now, Hamilton quaternions square to -1. The Pauli guys decide they don't want anything squaring to -1, they want it to square to 1. So they stick an I, you see, in front of Hamilton's quaternions, or literally stated as Hamilton's quaternion is an I put on the sigmas. And I just remembered I left an I out in some of the stuff that's about to come here. But that is a key thing. This imaginary number squaring itself to a -1, you see, is a big leap in faith. You see that Euler and others much earlier had done already. And so now we've got 3 things in quaternions business that all square to -1. Now you put i's on them and it comes back to being squared to 1, which is what we really want for what we're doing. And so you'll see them. But then we put the I back on it when we want it to do something. Okay, so that's what Pauli spinors do. They square up to +1. All right. And they make little cyclic groups, depending on what axis you're on. A little bit of the group theory that we saw before in a problem that you may have hated that had to do with 6-fold symmetry. Here's where they left the I out. I should have some I's in here. It won't make any difference for what I'm about to do here. But when I ask you to do this problem, remember, there's an I in there. And don't just copy off of this for that group table that's on the first problem. Okay, let's jump ahead over here. I'm going to try to keep these things keeping up with each other. The spinor components that you see there are X, Y, and Z. That's what the notation usually is, not A, B, and C. So you pick up any book on spinors, that's what you're going to see. Unless it's my book, then you'll see A, B, and C some places. Anyway, the idea is that I can take any vector, not just X, Y, or Z, any vector I can take, provided it's a unit vector. That little hat means it's unit for length, unit in length. Okay? That is, I want the dot product of that vector, which is a Pythagorean sum, 3 things now, to add up to 1. If that's true, then I could make a sigma sub A, and it will do the same thing as the other sigmas. You can make an infinite number of these sigmas by just picking a vector in a different direction. And idea is to try this out. That is, take sigma x, sigma y, sigma z, and just put numbers in here, arbitrary numbers, but make sure that the numbers square up to 1. They satisfy this. If they square up to 1, we'll use that in just a minute here, then you will get a square of this sigma sub A to be 1. And that's what's being done here. Now, again, some i's missing, but it doesn't matter because the off-diagonal ones that have the i's cancel. And you're left with that result down at the bottom. Let's see if I can go one step. It should have shown that. I don't know where I have it there. Let's see if it's on this one. I'm actually running two different versions here. I guess it isn't there either. Anyway, that's the basic idea, is that sigma sub a, any vector that's unit, will square to 1. Okay? But I'm going to go ahead oh, here we go. That's the result I'm interested in right there. And it suddenly showed up there and it wasn't there before. Okay. Now, here's the other deal. This is what I think Hamilton was really excited about. And that was that he was able to do the manipulation of vectors that involved something we were doing with complex numbers. Here I'm going to take two different vectors, a sigma A and a sigma B. These are arbitrary vectors. Here we're talking about x, y, and z, but pick any two vectors and see what that product is. Okay? And that is what's being written out here. And the idea is, and there should be some i's up here, but in any way, the little I here is the thing that makes this correct. There should be an I in front of, well, it should be right here. Okay. This is a cool thing. That is, if you put this together with these two vectors, the dot product sits in front of the unit operator. That's a unit matrix, 2x2 unit matrix. And then this is the sigma, and there's x, y, and z's in there, and they're each of the three components of the cross product. Now remember back in Unit 1, Chapter 10, when I said, hey, if you take a complex number and star it, and then multiply it by another complex number, these two different complex numbers, okay, you get this product right here, which is this, that's a dot product, and this is part of a cross product, you see. It's the xy minus yx part, the bottom one of this, the z one of this. And we had to put a little notation there to indicate that this cross product was not a vector, but a number. And then we play with derivatives and did the same thing. Okay? So that's what makes this cool, you see, because this has really gone into the third spatial dimensions. But it's even gone further. We're going to use it in relativity for space-time. And that's something Hamilton had no idea was coming. No idea. Okay. Funs and games. All right. There's one other thing, which I am just going to have you look at briefly on the problems. And that's the crazy thing theorem. There's the crazy thing, as crazy as I could make anyone look. I don't have enough hair on it to make it a trump. A trump didn't really exist when I was doing this, so you'll have to excuse me for not putting orange hair on there. But the idea is that if your crazy thing satisfies an equation that the square of the crazy thing, imagine squaring trump, I don't want to think of it, but anyway, the crazy thing squared, if that's equal to minus whatever you call 1, that is the unit operator, then the exponential of the crazy thing is 1 times the cosine plus the crazy thing times the sine. Now, we've already been working with a crazy thing. The square root of minus 1, or minus the square root of minus 1. It's also a crazy thing that does exactly this crazy thing, that it becomes 1 times the cosine minus I times the sine. It's just that this does it in 2 dimensions. These are 2 by 2 matrices right here. And it's minus I sigma, some component. Say A, I put a Greek letter there, but don't let that bother you. Okay? And I made it a unit vector because if it was a full vector that had lots of length to it, which it would be if it was an angle with many angles, many degrees, I divided by that, whatever it was, to make this thing with a hat on it. So that's something I want you to, take a look at. As I say, this assignment involves some reading too. A chance to use that textbook for something besides a door jam. And this business here, I don't mention a crazy thing in there, but here it is in the lecture. And we're going to ask you to explore it a little bit. Okay, now we're going to go off into the English land and talk about something Mr. Cayley did. Now Hamilton's in this story as well. And that is to study what it is that I have to do to take any matrix, but we're going to take a particularly weird looking one. It's not symmetric. I mean, it's got 4 different numbers sitting there, but it's only 2 by 2, so we can easily work the stuff out. And that's enough to show pretty much everything that happens when you do this miraculous operation called diagonalization that quantum mechanics absolutely has to have, or you're not going to do any business. So we're going to look through here first at a thing called the secular equation, and then the Hamilton-Cayley equation, and then things called projectors, and then things that square up to themselves, the kind of Ayn Randian in that sense. They're very solipsistic. The idea is that you just multiply yourself and make yourself again. Very weird. We're going to see those things in here. And then how do eigenvalues, that's the numbers that are the characteristic values of a matrix, turn into eigenvectors? You see, this is the one way to do that. And pretty much the only way, if you're going to have a big computer do it, would be following the prescriptions. Many or algorithms do this. And then there's some things here for people that like to do things like square roots of matrices, or a exponential of a matrix, or a logarithm of a matrix. This is all stuff that we can do if we play the game I'm about to play here. So let's keep things more or less in line here. Here's the deal. How do you find a vector that when multiplied by this matrix gives the vector back again? You can have it lengthened or shortened by a number epsilon. That's the eigenvalue there. But I want it in the same direction. I want this matrix not to change the direction of the vector. That's what it defines a characteristic or eigen, German, vector and the value that you have to lengthen when you do that. Okay? So the first thing you would do if you know linear equations is you say, hey, I can do that. I just bring this thing over on this side, and then I have a sort of what we would call the input function to a linear relation I have to solve. All I have to do now is just find the inverse of this matrix and multiply it by that, and I get the xy, wouldn't I? Well, there's a big problem. There's nobody's going to pay you for doing that, because what that's going to give you, and this is Cramer's way of doing an inverse. I don't know if you remember this rule, where you take the matrix that you're trying to invert, right? Put its determinant in the denominator, and then you replace numbers in the determinant according to what's over here on the right-hand side. This, this is something you ought to keep in your heads. It's really quick. This is a quick way to get a matrix inverse, certainly in the case of a 2 by 2. Well, the problem is that these determinants are both 0. And nobody's going to pay you for, you say, hey, I found a vector that works. It's 0, 0. Well, it'll work for any matrix. Okay? You're fired, as Trump would say. Okay? So we got to do something. What are we going to do? Well, this still might work if this is 0 as well. If this determinant of this thing right here, because there's epsilons in it, if that's 0, then it somehow might cancel this 0 and give you a number that you get paid for. That's the deal. That's what the secular equation is. The secular equation is simply demanding that the determinant of the matrix minus a number, we don't know what the number is yet, but we're demanding that that thing becomes 0, and then we could find the number. So I got to take the determinant of this thing, the matrix minus the unit operator times this unknown, epsilon, the eigenvalue, okay, of the energy, if it's quantum mechanics. This is where we get energies, quantum energies, all the time. It's solving this kind of equation. And the name secular equation goes back to the perturbation theory of orbits that were being done by the astronomers in the 1800s and 1700s even. So The determinant of this is not a hard thing to figure out when you only have 2 by 2 here. It's 4 minus epsilon times 2 minus epsilon, and then the off diagonals are product with subtraction. And that gives you this thing right here. This is the polynomial 8 minus 6 plus epsilon squared. And then this is the 1 times 3 right here. This 3 has to be subtracted from 8 to give me 5, and then I have epsilon squared minus 6 epsilon. I've got to solve that equation, and the equation is essentially being solved right there. That's the thing that results. Well, not quite yet. Let's go and do it here. This is a quick way. This is you guys in physics. You're going to do secular equations very often. They're usually going to be 2 by 2s on an exam. Just remember this coefficient right here is the trace with a minus sign. The trace of the matrix, 6 with a minus sign. That's this minus 6. And then the determinant of the whole matrix without the epsilon, 4 times 2 is 8 minus 3, 5. Okay, that's the 5 right there. Okay? Well, how do you do this in general? You're going to have an n by n on the computer. So here's your secular equation in general. Again, first coefficient minus trace, and then every other thing, all the way down to the determinant, is a plus minus, plus minus, plus, alternating sign, and then the sum of the diagonal k by k minors. Well, if you remember what minors are, this means something, but that is a very simple algorithm for setting up a computer to figure out the secular equation. Okay? Now, we want to do something else. And that is, we want an equation that the matrix obeys. And that's what is coming here. And that has a very famous name. Hamilton and Cayley, both very brilliant. Mathematicians, Cayley more a mathematician than a physicist. Okay. They both realized that if you take the secular equation, either factored or unfactored, every matrix, and this is something that's, I'm not going to prove that, okay? I can show very obviously, if it's a matrix of the kind we have in physics that is diagonalizable, it's trivial that this is true. But it's true for all matrices. So, well, let's say we need some faith here that this is right. And it is definitely right for all of the physicists' matrices, which are called normal matrices. But in any case, all you do is you take the epsilon and replace it by the whole matrix, and then the actual numbers, the little roots here, you put a unit matrix in front of that, so that you get, for the 1, 2, 3, 4 matrix, you get 1, 2, 3, 4 squared corresponding to the term epsilon squared in the secular equation, and 6 times the matrix is replacing 6 times epsilon. And the 5 sits there with a 5 in front of a unit operator. And then you write that whole thing up to see what it gives you. And you will discover that it gives you exactly 0. A 0 matrix, you see. This is a big fat 0 here that's coming to you. N by n 0 here, 2 by 2 0 there. Okay? Now, once you realize that this is true, that this equation is true, you can go and take the diagonalization problem apart in a beautiful way. And here's what you do. You replace, and there, say, are 1, 2, 3, 4, 5, j plus 1, dot, 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 down to n. In a n by n matrix, we only got 2 factors in our little thing there. So I'm going to only have 2 of these. I call them proto-projectors. You'll see what that means in just a minute. Here I have n of them. And what I've done is I've taken this equation, which comes out to be a 0 matrix, and pulled the first factor out and just replaced it by unit matrix. And the idea is that you're, in the case that we're looking at here, which is a non-degenerate matrix, you're guaranteed that the result without that factor is not 0. So you're going to get n things here that are not 0 by replacing every one of the factors in turn by a 1. And I put P on them because these are the things that give you the eigenvectors. And you'll see that in just a minute. So here all I did was replace the first factor here by a 1. So that's m minus 5 times 1. So here's the m with minus 5 times the thing on the diagonal. That's the 1 matrix. Okay? So I've got a minus 1 from that, and a 1 from that. The off diagonals don't change, but the on diagonals do. Okay? And then go on to the next one. Okay? This time I subtract the first eigenvalue to get the second projector. Here I take the second eigenvalue out to get the first projector. You're always taking out whatever isn't the one of interest. And here you're getting products of them. Here we just have two things to deal with. Very simple. But in any case, the idea is that when you get done doing this, these things are projectors and they contain in their columns the eigenvectors of this matrix up to a factor. In other words, those two both are eigenvectors of this matrix 1, 2, 3, 4. Okay? Well, you can try that out by multiplying 4 times 3 and 1 times 3. Okay? 12 plus 3 is 15. Okay? Well, that's 5 times 3. That's exactly the eigenvalue that we're talking about for the number 2 eigenvalue. And then number 1, if I do that same thing with this guy right here, I'm going to get 1 times minus 1 is 3. Now, why does that happen? What sort of magic makes that happen there and also here? Okay, so I'm going to keep these things up with each other so that we can discuss all of this. So what I didn't say before, what I'm saying in green here, St. Patrick says, hey, you got to remind people, here we're assuming that all of the characteristic values for this thing are different. That is, this matrix doesn't have some weird symmetry that makes them equal. And of course the matrices we're most interested in are the ones that do precisely that, so you have to be a little careful noting that whenever you do one of these problems. But if you look at your second equation and no repeated roots, you're in for this particular exercise. Okay? So as it says here, each of these little p's, these proto-projectors, we're going to have big p's, which are the real projectors in just a minute here, but the little protos satisfy this equation. That is, if I put back the kth factor that I took out here, here, or here, if I put it back, I have to have just made the Hamilton-Cayley equation and get 0, a 0 matrix. And this says that the matrix times the proto-projector is equal to the eigenvalue times the proto-projector. And that's what makes this work. That's the deal, is that this matrix comes up to this matrix and acts on the first column, and the first column comes out to be the same first column in this expression here, multiplied by the eigenvalue. So you get the eigen-equation repeated twice. Look at it for this one. Okay? This matrix right here times that gives me exactly 1 times that matrix. And this one gives me 5 times that matrix. Just erase one of the columns, say the first one here and the first one there, and you've got a ket equation. If you turn it around, which you can do because they commute, then the rows of these matrices, which in this case are different, are the bra vectors, eigenvectors. So we're getting two things for the price of one here. I don't know any quantum mechanics book that does this because they don't give a damn about the bras. All they're interested in kets. Okay? Sexual, what do you call it, chauvinism. Turns out the bras are really important when you're doing group theory, okay, which is what we're headed toward here. That is odd faith, of course, that I've done so much with group theory, I'm willing to sell it with a loud voice. Okay, so that's the situation we have. And this would be enough right here to do what we really need to do today. But I want to finish this, because this really gets very elegant once you realize that we have to take advantage of this commutation of the matrix with itself. That is, the matrix is going to commute with all the powers of the matrix. That's obvious, and matrices are notorious for not commuting with ones that are different from them, but when they're the same, they certainly do commute. Okay, is this making sense up to this point? I want to make sure that you see what's going on right here, because in the next step, and there it is, I want to turn the little p's into big P's. Things that when multiplied by themselves give themselves back again. The only thing that I know that does it is unit matrix, but there are lots of things that do this. It's called idempotent, not to be confused with impotent. These things are very potent. Okay, so let's see what it is that is involved here to make that happen. What I do is I say, okay, here's my protoprojector J and here's my protoprojector K. The way you should write these things is as a product of M minus all the eigenvalues except for the one that you're interested in. So this is saying make a product of every one of the M minus epsilon 1, 2, 3, 4 times unit terms, but forget about the one you took out, which is the one you're interested in for that particular pk. Then pj is just the same thing, a product leaving out the j's. Okay? But right now we're just going to let pg go through and hit m right there. And we know what that happens when p hits m, it just gives eigenvalue j in this case times the original p. So that makes this thing right here. Okay, and this thing is the pj times 1, so the two pj's can just be taken outside, and this little factor is sitting there. This is a number now, not a matrix. There's the matrix. Okay, does that make sense? Because if I take this thing now and divide both of these by it, that means I've got this thing over the same factor, then I get these big P's. That's what the definition of an idempotent matrix is. Okay, so I get something that satisfies that green equation there. Okay, idempotent means P times P is P. Right? So the basic idea is that by sticking this thing in the denominator, I get a great big P, which looks like this. And this is a real easy formula to remember. It's a matrix minus eigenvalues, just like what we had, except for the m equal k. And then this is the epsilon k minus all the other eigenvalues. And that'll never be 0 because we said there weren't any one of this is the set in any repeats, any symmetries in this particular example. So here's the first one, and there's the second one. So there's that matrix, but now it's got a 1/4. That's 1 minus 5 in this case, and 5 minus 1 in that case. That's where you get the minus signs when you turn the thing around to make it both 5 minus 1. Does that make sense? Okay, so it's the properties of those things, the big P's, the uppercase P's, they're going to make this really elegant. And this is, as I say, something that should be taught in high school, at least for the advanced placement. Okay, so the deal is these things still satisfy their eigenvalue. Putting a number in front of them is going to change that. Once you've got an eigenvector, you can multiply by 17, it'll still be an eigenvector, just might not have the norm or shape, length that you want. Okay. Now one of the things that you do notice is P times itself gives itself back again. Again, it's very much like Ayn Rand, a woman who believed that when she died, the whole world ended because she was the whole world. I don't know if you know that about her, but she's cuckoo. Anyway, here, when Ayn Rand comes to anybody else, it gives 0. Any one of these is different, you get a 0 matrix. And why is that? Well, that's because the factor that this one is missing is picked up by this one. They all commute, and as soon as they get together, they make 0. That's the Cayley equation. But if they're the same, if j equal k, it gives back number k. Okay? So that what we're beginning is a really elegant way to see all of this stuff in quantum mechanics about orthonormality and completeness and things like that. The functional analysis is so awfully difficult for students this first time around. This is a way to get a look at this. So, I'd like to show you the pictures of the thing. First, before we draw the picture, let's do a little bit more algebra here. What I can do is I can take this number that comes out in front here, that's the denominator, came from that and that, and came from that thing right there. I can take that number, get the square root of it. And then I can put this vector here with this right here divided by the square root of 4, which is 2, and then this number right here divided by that same square root of 4. I will have produced the direct version of a projection operator, which is what it gets thrown at you when you see in quantum mechanics. You see this ket bra a lot in modern quantum mechanics books. Okay? This is how you produce that, right there. That's how you make it. And then you start to look and see, what do these vectors look like, this bra and this ket. And then that's for eigenvalue number 5, the 5 eigenvalue. The second eigenvalue was 5 here, and the first one was 1. Okay? What do these vectors actually look like? And this is really cool, you see, because we're doing a matrix you won't run into very often in quantum mechanics, not in the standard quantum mechanics. They're all Hermitian. These numbers have to be conjugate of each other and equal in that sense. This is an oddball matrix, but this method takes care of it. It makes two sets of vectors. The blue vectors are the normal ones that people work with that get hit by operators from this side. The other ones are the bra vectors that get hit from the other side. They're rows. They're rows. They come out of the rows of these projectors. And look at the relationship between them. First of all, ket 1 is not the same direction as bra 1. In quantum mechanics they are, except for conjugation, always the same direction. Which means they're not really the same direction. And then here, same thing, they're different. But they're right angles to each other. The reds are orthogonal to the blues, and the blues are orthogonal to the red. And that's this relationship right here. Because the rows in this projector are multiplying columns in this vector, right? And that's making 0 in every case you do it. This is a beautiful linear duality. And as I say, I've repeated those equations on the side here just to indicate that that's how they go together to make the actual projector. Okay. Making progress here. Moving along. The next thing I want to show you is what this is really two cases of. This is what is called orthonormality, the zeroing when you're not the same. And then there's something called completeness. It's really weird when we do it this way. This is something that really makes this wonderful. In any case, what's happening here is that when we take the blue vectors and do brackets, only the ones on the diagonal survive. That's the actual definition of orthonormality that you get when you just look at, from a point of view of wave functions or vectors, which are functional analysis vectors. Okay. But there's something else going on here that is coming up. And that is, instead of doing a product, do a sum. This always gives 1. Wow, that's really cool. Now this is Dirac's way of writing it. And when you flesh it out, it becomes what is called the completeness relation in functional analysis. But here in algebra, it has a beautiful sort of difference with this one. When you look at it the functional analysis way, these just look like two sides of the same coin. But when you look at it from an algebraic point, it's really different. So, we got to make a fuss about that. Okay? And then something new comes up that lets us take a matrix and do anything you want with it. Okay? So, we have already said the brackets are orthonormal, and the next stop is this weird result. Okay? And you can see it's happening. You can see that if I take big P1 is this guy right here, and then big P2 is this guy right here, okay, or that way, or that one. Well, let's look at that one because it's easy. It goes a quarter. And I add them up, I get 1 plus 3 is 4, that's a 1 in that place. I take this guy and that guy, they cancel, this guy and that guy, they cancel, and then this is a 3 plus 1, that's also 4. I am ending up here with the unit matrix. And that when you say, oh, that's an accident, that can't be. What's amazing about this, using these formulas, is this is true. This sum is true of these things, no matter what numbers you put in here. You don't have to put the eigenvalues. This relation is super true. Now this is discussed at the very end of this lecture, which we won't get to, but I challenge you to look at it. It's really quite cool. Now, we can do something that's very powerful. Remember we wanted to take a square root of a matrix? We're ready to do it now. Okay? You see, the basic idea is, if this thing all adds up to 1, and I reapply the original matrix that gave all these things, I then get a bunch of eigenoperator expressions, right? I then get that I get an eigenvalue in front of each one of the projection operators. That's called the spectral decomposition of an operator. All of its spectra are displayed with the vectors that contain the eigenvectors. That's so very elegant. But it's also very powerful. Because if I square this matrix, for example, now it's easy to square a matrix, so you probably wouldn't do it this way, but if I square this thing, you see what's going to happen is I'm going to get epsilon squared times p squared. But p squared is p, right? And I do the same with all the ones. But what about p1 times p2, right? You get cross terms, right? Wrong. p1 times p2 is 0. So all you get is diagonal terms. Therefore, the square of the matrix is just the sum with the eigenvalues squared. The same p's are there. I do another power, same thing. I do a power series, I get a little power series in each one of these eigenvalue places. So any function of that matrix that has a power series that's definable, that is, if each of these things exists, that's the way you take any function of a matrix. Any function that can stand to have an eigenvalue put into it without blowing up or doing something weird, you can go to 0, that's fine. But infinity makes you, kind of stop things, right? So if these functions are definable in the eigenvalue domain, you've got that. So here's what you can do. Take 1, 2, 3, 4, and I say, okay, I'm busy, I want to talk on my cell phone, so I'm giving you this problem. I want you to multiply this matrix by itself 50 times. I'll keep you busy for a while, right? Unless you know the trick, which is to take 1 to the 50th power times the first projector of the eigenvalue 1, and then the second projector of eigenvalue 5, you take 5 to the 50th, and you add them up, and there's a closed form answer. Isn't that cool? You just save an hour's, it's this kind of thing that Gauss used to do. His teacher would give him some exercise, that was going to take all day, right? And the teacher figured go out and read a book or smoke some hashish or whatever, and before he could even get out the door, Gauss says, hey, I've got the answer. Okay, well this is that kind of thing, you see. Very powerful use of these projectors. Now, square root of m, no problem, right? Well, as I say in your exercise, when you do this, you got to be careful, because there's a whole lot of square roots, not just 2. Each one of these can have a plus or minus sign on it. But that does give you the square root when this is all said and done. Okay, And that's the thing you want to test, of course, because you can obviously make an arithmetic mistake. All right, now we've got enough time here, I think, that clock is right, to do this stuff. Particularly this one. This is about as long as this, but it's a whole different way to approach eigen solutions. And the idea is that when you have a problem that has some symmetry, and you can describe all of the states of that problem by symmetry operators, that is, operators that take you from some origin that you've chosen more or less arbitrarily, and sort of like taxis, they're the things that move you there, but you can also label the actual locations. And that was the exercise I gave you with a hexagonal structure. Okay, that's a typical situation. Say a bunch of quantum dots that have little pathways that connect them, let tunneling happen, and you want to find out, you know, what's that? What kind of weird oscillations is that thing going to do? What could we make it? And what would its spectra be? You see. So that's what we're after here. Only this time we're working with just all of these little operators that are, in a sense, symmetries of things that have spin a half. That's one thing, or any quantum two-level system. So here's that expansion again, written in a couple of different ways. Instead of having projection operators in here, we've got these operators that square up to 1. The sigma operators, the spinners, the Pauli spinners. And what we'd like to do is make use of those properties, the multiplication properties of this, and the group structure of this. And the idea of the, I think, of labeling things with group operators is that once you've done that, the group knows everything there is to know about the dynamics of that system. It's basically solved Feynman's most difficult problem, which was to find what are the appropriate classical paths and how should I use them, because there's so many of them, too much of them. What do I, and they're undoable in a sense in most systems. In this case, you have all of that nailed. All of that is defined. Where things are and how they get from one to the other are all defined by a group. So that's what's really happening in order to make this powerful thing that we're going to do with this work. But in order to make it work, you have to make things equal to 1 wherever possible. So the first step here, as it says over there, is to divide by the actual length of the vector sum. That is, this is a 3-dimensional vector with 3 components, so I'm interested in dividing by its length, its triple length. I'm just labeling here whimsically A, B, C, D, but really only the 3 numbers that correspond to this. We can sort of leave the unit matrix component out of this and tack it on at the very end because it commutes with everything. It just sits there and adds 1 extra factor to everything. Okay, so this number is important right here, and we're going to divide by it so that we get unit spinners. And you know how that's a good thing to have. This dividing that, okay, is equivalent to dividing that. B is equal to that, C is equal to that, A minus D over 2 is equal to that. So we're putting here things so that when I square up this spinner, I get 1, not some number that would be that frequency. That we just want to tuck that in. So I'm putting a little hat on all of these coefficients right here. So they're just these coefficients divided by their length. And then this thing has to be divided too, but remember, it's something that we added in at the very, very end of our calculations here. Okay? So this is what we're looking at. We're looking at this little unit guy times this particular A spinner, this little B unit, B spinner, and C spinner, Okay? Asymmetric diagonal and bilaterally balanced, and the hero of the day there, the St. Patrick's operator, which is the green chiral, means go, current. Okay, and that's the new thing here. As I say, if that's all you guys, you don't need this. All right, so I'm going to put these all together. Okay, and then I'm going to have this thing times a unit operator. This little thing here will just be this whole expression. That's going to be tacked on at the end. Okay, I put a caret on it. It's not really unit. This thing right here is some other value, but just to keep the notation more or less the same. It's part of a four-dimensional vector is what it really is, but we won't be getting to that until a little bit later. So there's what we're dealing. We're taking all of this stuff and working with that matrix. Okay, and if we do that, this matrix right here, this is what I'm talking about, this whole thing right here, forget the little tag or honor there. Okay, this whole thing I'm just going to call H, little Hamiltonian, little unit Hamiltonian. Okay, and that little unit Hamiltonian is sigma dot a vector that has unit length. That's what you get when you divide this into each of the components. Okay, this thing has a Hamilton-Cayley equation. It's very simple. H squared equal 1. And everyone knows how to factor that one, right? And I'm just factoring it in the operator form here. H squared minus 1 equals 0, okay? That's H squared equal 1 with the 1 brought over on the left side, okay? It's H minus 1 and H plus 1. No worry about commutivity here. 1 commutes with everything, okay? So there are our projectors. At least we don't have them normalized yet, but they're ready to be normalized. They need a 1/2 to do the job. So you're going to get a first eigenvector projector here that's 1 minus h over 2, and its frequency is going to be this frequency right here, but you've got to tack on that thing that's hanging off on the right-hand side. And then the other one will just be that frequency subtracted. So there's your two-level system completely filleted and solved and ready to use. And we're going to use it. We're going to, I hope, look at some nice animations of what this gives. Now, just to refresh you, I've written it on the board here. The idea is that h squared minus h is equal to, well, it turns out to be minus h plus 1. And then this one has a similar thing. But that's a projector, a proto-projector. That's the other proto-projector. Here are the two eigenvalues, plus and minus 1. We already knew that's all we're going to get up here. We divided it out so that we got unit values for this particular sigma with a hat, omega with a hat. Okay, so that's the key to this right there. That you have the projector sort of just, in a place where they can give you the actual eigenvectors. So what I'm going to do here, you see, is produce an equation based on these three numbers. Okay, and these three numbers, again, are right here, here, and here, and they're just these numbers divided by that. Okay, so I can go up here and just look up those numbers and figure out what it is that I need to set on my phasor. This is the first phasor. The x is the circle horizontal, and then the imaginary part is up. It's, from now on, we're going to be calling that a momentum. This is an action, a variable here, involving coordinate and momentum. It's phase space. So I get the values for these four things, and that's something that I'm asking you to do in a problem in a slightly different way. But when I do that, this is what I have to get. This is the projection operator that we're talking about right there. That's just 1 minus h, and h is this whole matrix right here. So I'm just looking at the first column. I'm just looking at omega a at plus 1. I've got to put an eigenvalue still on that projector. And then this doesn't change at all. And then I do it with a -1 right here. That doesn't change at all. Isn't that elegant? I mean, it looks like it's a total trick. But it is a very nice trick. Now there's some geometry that goes with this. And that geometry is that each of these components, which we'll see in our animations, is a vector that really is a crank. It's this vector right here. What we're looking at is an omega vector. And the very most fundamental motion in all of nature that just requires 2 quantum dimensions is the motion of precession, where the operator comes with its suction cup, so to speak, in the mechanical analog, and sticks on that sphere there and then rotates it, which is quite a complicated motion. As you can see, all the little dials have to change in different rates and do all sorts of fairly complicated stuff. But this is an embodiment in a mechanical way of what is going to happen when we let time go with this omega, and then what's called the Stokes spin vector, because it goes back to 1864 when John Stokes figured out how to use this stuff to do optical polarization, which is an example of a 2-dimensional oscillator with 4 dimensions of phase space. So you're going to see in a 3-dimensional real space a spin vector whirling around in general. But when you want to see an eigenvector, you take that spin vector and let it hide on the axis where it doesn't have to get swung. It's like going into a port and having a beer, and you're just sitting there. You're getting a little twist to you, but then, you know, a vector doesn't feel a twist. It's just a line. And you can put it either up or you can put it down. Those are the 2 possibilities for measurements of a quantum system: spin up and spin down, in what we now call spintronics. How many people know about spintronics? It's replacing electronics, because now we're so sensitive in measurements that with the electrons going through now can carry spins and be doing this kind of motion all the time. So here we are doing that calculation in a very elegant way, the dynamics of that. Now, admit, I'm not yet wiggling the crank. If I start wiggling the crank, that's a nuclear magnetic resonance. That's the way you resonate things. And you do it like an Olympic, you know, whatever you call it, what do they call it, the throw, the hammer throw, right? You spin around and always ahead of things, just like the force is ahead on the phaser, and get things going faster and faster and faster and faster. And it does other things too. It turns and processes and all sorts of stuff. So that all of that stuff we know available by following this fairly elegant path. Okay, so let's look at this in piece by piece. And we've got about 15 minutes to do this, but it should be enough to see. And I'm going to try to do it on both screens so we can compare the 2 things. First of all, we'll compare an A-type matrix. So you see what I've done is I just zeroed out everything except the A. Okay? This is the only thing. This is Hamiltonian. It's just going to be that. Okay? It's already diagonal, so what's the problem? Well, you want to see the trivial case first, and it's not that trivial when you actually see it happening. But it is going to be equivalent to having a crank vector, this thing laying right down on the x-axis. I'm sorry, actually on the z-axis if you use the old notation, but on the asymmetric diagonal axis. And in other words, that's why this matrix is asymmetric diagonal right now. And it's the one that's going to be swinging a spin vector in the animation if the animation works. And there it is, ready to be clicked. Okay? In the other screen, we'll do the other one that's real, and that's the B-type, bilaterally symmetric. So you see I've zeroed out everything except the B, C's gone and A's gone. Okay? You still have that thing, but all that does is add an average frequency to the ups and downs that are going to be coming out of this matrix right here. So we're going to have a crank here that's laying in the same plane, so it isn't that different from the A, and any other direction is just, you know, another direction in a two-dimensional plane. But still, this one is the one that we've been talking about. And if you only do our coupled pendulum thing, you never get out of this plane. You have to put some magnetism or some, you have to put the thing on a rotating table or put something that has a chirality, a cyclotronic motion, to get this stuff. And that will do last. Okay? All right, so let's see what this one looks like, if we can be so brave as to click this simulation here. Let's see what happens. That's the motion. Swinging the spin vector around the A-axis, okay? Now this one, I can find the eigenvector just up front right here. All I have to do is click right here and stop the motion out, up, and down. Boom. That's the slow slope. There's the potential behind it that would be in the mechanical system, okay? And it's very gentle. It's very slow, okay? And there's nothing going on for the other one. Let's, whenever you do this, let's just erase everything, and you can see what's up, okay? That one's moving. This guy right here corresponds to the phasor that sits opposite the x-axis, if you will, the number 1 axis. The other phasor that sits opposite the y-axis doesn't have anything going. But of course, if I go here and just click it right here, then I can get that going, right? And right now we have a frequency of about 2 to 1. Now this is the frequency of the classical oscillator here, so you got to take the square root of this. This is frequency squared. So you're getting a 2 to 1. Okay? Okay, now anytime I go on this thing right here, the spin vector is up on the A-axis. Anytime I go, and let's erase things just to make sure that's clear, anytime I go on this axis, is the other eigenvector that we have, it's spin down. And I didn't quite get it on the axis, so you see a little quivering going on there. Okay? It's got a little bit of this motion in addition to the big motion that you see on the advanced slopes. On the advanced slope, it's really going there. Okay, compared to what it would have done. Otherwise, this one has just a little bit because I didn't quite get it on the zero there. Okay? I can always do that to make it have some. Okay? All right. So that's what you get if there's no spring between these objects. There's no connection between these. They just have their own frequency. This one slow, that one fast. Pretty simple, but yeah, that's kind of pretty anyway. All right, let's go over and see if we can get this one cranked up. This is where we do have some coupling. And I forget how much, but we'll soon find out here if it works. There we go. Now you can see the spin vector is being rotated around the b-axis. And now we have that 45-degree, remember, southwest to northeast bunny slope, and then the what I'm seeing here is a faster motion there than I do here. Let's see what my values are here. B is positive. When you play with this thing, it's probably better to do what nature does and put a minus sign on that. So let's change that so that it makes sense compared to what you'll see in the textbook and what we showed last time. What I can do here is I can go over here and put with my control click or right click the wonderful transparent panel that TC's come up with here. And what I'll do is I'll grab this thing here and jerk it a little bit this way, And as you can see, it really makes a very complicated thing. There's a plus, there's minus, and I'm going to go ahead in here and stick a few zeros in there, at least one zero in there. 0. Okay, now it's more brought back to earth, so to speak. But it's doing exactly what the original was, with a minus sign on it. Let me go ahead and click it away, and we'll go ahead and erase the paths. And here is the beginner slope. It was the advanced slope before with a plus sign. Now it's the beginner slope. So that's a low frequency mode that's symmetric. Remember when the two pendulums swung together? And then the other possibility here is on the advanced slope. That's a little faster. Not much faster. You can see that one of them is 0.912, that's the square root of that, and the other one is 1.88. That's the fast mode that we're on right now. So there's the B-type motion. Now, each of these corresponds to a spin vector that is in the plane, in the equatorial plane, AB plane. Okay? The other one was on the A, this one's on the B. And the advanced slope, let's erase things so you can see what's going on there. I'm going to erase the paths, and then I'm going to switch from the advanced slope where the spin vector is over there, and if I'm a little off of the spin vector, of course, it'll be a small rotation around the negative B axis. That's the anti-symmetric motion that we're talking about right now, where these two go together and pull apart. That means the spring, whatever it is, very weak spring, is affecting the frequency and making it a little higher for this mode. Okay? And then the other thing for the spin vector, you see that spin vector is really a cool way. It's just getting rid of all this complicated stuff and just showing you the simplest possible precessional motion. If I go onto the beginner slope, the spin vector is switched, and if I'm not quite on the beginner's down fall line, and the more off I get from it, the more the spin vector will oscillate. And let's erase paths here and just look at this motion. Okay, so you see there it's precessing around the b-axis. Now this is really paradoxical in some ways, the connection between classical and quantum. The most difficult mechanics, which we haven't even covered yet, is the mechanics of rotation. Okay, that's my field. I'm afraid to talk about it because people don't understand what you're doing. But the motion that happens when you spin something and it precesses is really complicated. It doesn't have to be. We've got simple ways of looking at it, which I can tell you about, and that's why I'm a leader in this field. But the idea is that the simplest possible motion in nature is, that's it. That's where you start. Everything is built out of that. Put another level in there and you've got it 3 times. 1, 2, 3. Put 4 levels in there. I've got a whole bunch of pairs here. Each one of those pairs is that. So there are a whole bunch of things doing that. Think how many there are that are making you stay alive and take this course. Okay, now we got one more to go here. Not quite up by our 45-minute time limit, which is pushing it, right? What I want to do here is go back, and I'll go back on this one because I want this to show up nicely. I want to go back and pick up the next one. This is what we've been doing. I'll skip over this stuff. You should take a look at this and see why it remains 90 degrees apart in that case. But let's do the green. St. Patrick's Day, we can't leave out the C, the green C, the go-go of this whole business. Let's see if I can get it going. There we go. Now, what you're seeing there is a really fast focal pendulum motion. Museums have, in their central hall, almost all of the major museums have a focal pendulum somewhere in the Science Museum. Big pendulum, okay? And every day some guy goes out there, usually if it has sand dropping out of it, they make a path, but sometimes they don't even have it. It brings this 100-pound weight out to about here, right? And lets it go, and it's a very high Q oscillator, can last until closing time. And if the Earth weren't rotating, it would just keep going this way. But it doesn't. It does this. This is focal resonance. Again, a fairly complicated effect. But as far as spin goes, it's just a spin vector. This time I've got it as far away from the eigenvector as you can possibly get. Instead, I'll go in there, if I can get the right mouse here. I'm going to send the thing in this direction. And that's going to put the spin vector almost on the c-axis. That's right circular polarization for a light. Very close to it. It's got a little bit of wiggle, and the s vector is precessing a little bit. And you guessed it, going the other way. See how good I can hit it. I'm not sitting right there, but I can look here. I think if I put it right about there. Yeah, I know you can click. I don't want to cheat.
No, I mean you can. Oh, okay.
Okay, now I've got left circular polarization. You see? Okay? So those are the two eigenstates of this particular Hamiltonian. And we're talking about light here, and we're going to be talking about light. That's what we're going to build our relativity and quantum mechanics out of, this one. Running into each other. Okay? Okay, so these are really simple ones. This one just has C turned on. Now, I made D and A. It's like DC made D and A equal to 1, which is fine, because they now have frequency. Otherwise, things go backwards automatically. Okay. But I hope this gives you a little bit of a picture of the quantum world, as well as the classical one. And the mechanical one. What more could St. Patrick want?